So read this question. In this question, right, a block is a horizontal slab, right? Suppose this is the big block, all right, this is the capital M and the small m is placed over here, right? This is the same question you have sent me as a doubt, right? And the friction coefficient between the block and the slab, right? This is a slab and this is a block. The friction coefficient is mu. If block is not separated from slab, then determine the angular frequency of the right. So we have to find the angular frequency. Listen one thing. Suppose this is the block, right? And it is placed on hand, and with my hand it is moving left and right, right? If I move my hand very fast like this, so it will slip from my hand. Are you getting? Slowly it will move, but if I increase the frequency, then once right after some time it will, for a very high frequency, it will not move with my hand, rather it will slip from my hand. You understand or not? So how it is? Listen, if you stretch, right, if you stretch a little bit, suppose there is a elongation, all right, suppose the amplitude is A, right, amplitude is A, and this is the mass M, right, this is the capital M. Tell me what is the maximum friction available? Maximum friction available. What is the maximum friction available? Tell me. Here the maximum friction available is mu into N, and N will be equal to what? This is mg, this is normal. So N will be equal to small mg, and this is equal to mu into mg. Are you getting or not? Right. Listen one more thing. If this is the pen on my hand, when it is moving towards right, can you tell me which force is taking it towards the right direction? You tell. If this is the plank and this is the mass M, and this is the plank, suppose this is the plank or my hand, and it is moving in forward direction like this. So can you make the free body diagram of this? Tell me. This is the small m. If you make the FBD of this, the mg will act upon this, normal will act upon this, and it is moving, suppose, with some acceleration A. So what is the force acting between the two surfaces? Which force is taking it in the forward direction? Friction. This is the friction is acting over here. The static friction will be there. Are you getting or not? What is the maximum value of this static friction? Say mu into N. So when it is moving left or right, this, if you consider this FBD, the friction is only the cause which is taking it from left, right. Are you getting or not? So you tell me, when it is at maximum displacement from the mean position, what is the acceleration of this block? You tell. The acceleration of this block m and small m will be the same because there is no relative motion. But if you consider at this position, the maximum acceleration will be when it is at extreme position, and the maximum acceleration will be in this direction. Are you getting or not? Now it will start moving in this way, right? So tell me, if the maximum acceleration is there, so the friction will be acting Fs over there. Are you getting? Because it is taking towards right. When it is moving in this way, the friction is always, listen, it is moving left or right, it does not matter. It matters where is the acceleration. Along the net force, the acceleration is over there, right? So if it is at this point, the static friction is acting over here. So what is the static friction? The maximum acceleration is, suppose, a omega square, which is provided by what? Which is provided by this static friction. So if this friction is what? Say m into a, right? What is the a max? The a max is a into omega square. Is it clear or not? Right. This is the static friction which is acting on this particle, on this block by this lower plank in this direction. And this static friction is always, it should be, what is the condition so that it does not slip? The condition is that this static friction must be less than the available maximum friction, right? What is the condition? Condition not to slip. Condition not to slip. The static friction between this block must be less than maximum available friction. So what is the static friction at this point? Say m a omega square less than Fs max is what? Say mu mg. Are you getting or not? M will cancel out. So the omega square must be less than mu g by a. So the angular frequency must be equal to mu g by a. Or let me check what is given. Okay, so this must be the angular frequency. So the minimum frequency, the maximum frequency is that. The frequency should be less than this. Less than this mean below this every frequency is possible. Right above this no frequency is possible. If the frequency is increased, the required friction will be less than the available friction and the block will slip. So what is the maximum allowable frequency is root over mu g by a. All right, copy this. Read this question. In this question, a block of mass m, right, this is the, suppose the spring of the spring constant k, it is suspended from the spring constant. Now find the amplitude if it is released. Listen one thing. In the NLM, we had completed, we had explained this earlier, right? But now again I am doing this question. It is a very important question and chances are there the question may be asked, right? In the work energy theorem also the same question we have done. Suppose there is no elongation or compression in the spring, that is the spring is in natural length and this is my hand, right? If I remove this support immediately like this, so what will happen, you tell? Right, tell me what will happen if the support is removed? Because of mg it will continue to move. What is the acceleration right now? The spring force is 0 and the acceleration at this point will be g, because mg is the force acting downward. Mg upon m is equal to acceleration, right? The net force is equal to m into a, force is equal to only mg upon m. So at this point the acceleration is equal to what? A by g. And because of this acceleration what will happen? You tell. The velocity will increase. The velocity will increase, continuously increasing. But listen one thing. After some time, right, the velocity is increasing. You tell me, if after some elongation the spring force start acting over this, are you getting? And mg is this. This is the spring force. You tell me, suppose this is the kx now. Suppose this is the x distance. So spring force is what? Kx. In this case, if, right, kx is less than, or you can say if mg is still greater than kx. Mg is still greater than kx. Tell me, what is the acceleration of this block? Say downward. Are you getting or not? You tell. Varsha, the acceleration will be downward or not? Yes. If it is acceleration is downward, now what is the acceleration at this point? Say g. The acceleration is a1. Can you tell me what is the acceleration of a1 over here? a1 is less than g or more than g? The net force here will be equal to mg minus kx, and net force is equal to m into a1 is equal to mg minus kx. So a1 will be equal to g minus kx upon m if you divide by m. So the acceleration is reducing. Acceleration is reducing. The acceleration is reducing does not mean the velocity is reducing. Here the initial velocity was 0. The velocity will increase till it will increase if it has the acceleration. Sometime what will happen? There will be so much elongation in this spring. Suppose the elongation is x naught, such that if this is the mg and this is the kx naught, this is the called the equilibrium position. So mg here become kx naught. So the net force is what? Say 0 in this case, right? The acceleration is 0. So at this point the acceleration 0. Are you getting or not? But from this point to this point, here the mg is greater than kx from here to here. So acceleration is downward. So velocity is continuously increasing. Here the velocity was 0. It will continue increase. The acceleration become at this point 0, but the velocity is maximum. Are you getting or not? And because of this maximum velocity obtained, right, it will continue to move further. Are you getting? It will continue to move further. Right, now it will move further till the velocity become 0. From here the acceleration is in this direction, the velocity is increasing in this portion, but now when it further comes down, tell me, if further comes down, in this case the spring force become greater than mg. Right, I'm making this figure. Suppose this is the mean position, the equilibrium, mean net force is 0. Now if you consider this the mg, right, and this is the kx, what is the x now? The x is this elongation, x naught plus this elongation. Are you getting? In this case the kx is greater than mg, and therefore retardation occur. Are you getting or not? Retardation occur mean it's a velocity. The retardation is a velocity is v this side. Velocity is v this side. Are you getting? But it is reducing. Why? Because kx and mg, kx is greater than mg, and the acceleration in this side. Are you getting? Velocity is continuously, velocity is reducing, is decreasing, you can say. All right. And finally, what will happen? Tell me, what will happen? Finally, suppose this is the mean position. Here, the velocity becomes 0. Right. So it is the initial position. Initially, it is increasing. The acceleration is downward. Velocity is increasing. Here, the velocity become maximum. Then what happened? The acceleration is in this direction. Why in this direction? Because in this case kx, I'm writing here, right, the acceleration is in this direction, kx in this case is greater than mg, and therefore retardation occur. Is it clear or not? After some time, if the velocity is continuously decreasing, the velocity of this block becomes 0, and this force, right, kx, if this distance x naught is the mean distance, right, this is the x naught, you will see this is again x naught. In the work energy theorem we have done, I can also done here now, right, and the kx, this is mg, and this force is greater than mg. Now it move further. So therefore, if you release this, if you remove the support, the block will increasing its velocity. The velocity become maximum. Because of this velocity, it move further, but the speed is reducing, and finally the speed becomes 0. Now this force kx is greater than mg, and because of this force, the acceleration is in this direction. Now it will move further, velocity become maximum, the velocity become again here 0. So it start oscillating like this. Are you getting or not? So it is performing simple harmonic. If you remove this, it perform start oscillation about this mean position. Is it clear or not? And what will be the time period? Time period will be root m upon k, no doubt is there. Right, this is the time period. And what is the amplitude? Tell me. This x naught is the amplitude. This is the mean position, right? This x naught is the amplitude. What is amplitude? Amplitude is x naught is equal to, right, mg upon k. This is the amplitude. Are you getting or not? Copy this. So what is happening here? If you remove the support immediately, it will start oscillating, right? It will be the mean position. Mean position means this is the x naught. Mg is equal to kx naught. So the x naught value is equal to what? Mg by k. Further it will move by distance x naught, right? And this is the plus a, or you may assume this is the minus a. It will perform oscillation with the time period will be 2 pi root m upon k. Are you getting or not? Listen one thing. In the work energy theorem, we have done one more question, right? If this is the block, suppose, right? This is the block, right, m, and this is the support. This is the support. Support comes down slowly. Then what will happen? Tell me. If this is your hand, and if you bring the support slowly, not immediately removing, so what will happen? It will come down with your hand. It will come down, and at this point, at the equilibrium, right, there will be sufficient spring force, right? At this point, the x naught will be there, right, such that the mg and kx naught are equal. All right, so kx naught is equal to what? Say mg. So x naught is equal to what? Say mg by k. So this kx naught will balance the mg. When you are bringing down it slowly, your hand will move down and it will remain in equilibrium over here. So if it comes down slowly, it will be at rest. And what is the elongation? The elongation in this problem will be the x naught is equal to mg by k, and your hand will go down. Understood? But if you remove this support or your hand immediately like this, so what will happen? It start oscillating. And in this case, what is the maximum elongation? It start here, it move fast, velocity is maximum, it becomes 0. So what is the maximum elongation in this case? They ask this question, say 2x naught. In this case, it comes down slowly, the elongation is mg by k, the maximum elongation is 2 mg by k if support is removed immediately, right? Is removed immediately. Are you getting or not? Right? Completely, right? Or you may write completely. Fine. So this is the difference between this part and this part. If you want to copy, you can. Okay, so read this question. In this question, given that periodic time oscillation is T1, suppose the spring constant is K1 and the mass M is hanging. So its T1 time period will be 2 pi root, right? T1 is equal to 2 pi root M upon K1. Now the same mass is suspended from the another spring, having the spring constant supposed to be K2. In this case, the time period is 2 pi root M upon K2. All right. With the T2. Now if the same mass is suspended from the series combination of above two springs, now these springs are taken in series. Are you getting or not? Suppose this is the K1 and this is the K2 and this is the mass. So now the T dash will be equal to 2 pi root M upon K equivalent. And what will be the K equivalent here? The K equivalent is 1 upon K equivalent is 1 upon K1 plus 1 upon K2 like this. Are you getting or not? So in terms of T1 and T2, we have to find the relation, right? Okay. From here, if you consider the T is equal to 2 pi root M upon K, make the square, right, M upon K. So what is the 1 upon K? Tell me. T square upon 4 pi square M. So 1 by K value is this. So for this case, 1 upon K1 value is what? It is equal to T1 square upon 4 pi square m. What is the 1 by k value, 1 by k2 value from this? 1 by k2 value is T2 square upon 4 pi square m. Is it clear or not, you tell? And from here, what is the 1 by k equivalent value, you tell? Is equal to T dash square upon 4 pi square into m. And what is the relation between 1 by k1, 1 by k2 and 1 upon k equivalent? 1 upon k equivalent is equal to 1 upon k1 plus 1 upon k2. The k equivalent is T dash square upon 4 pi square m is equal to T1 square upon 4 pi square m. This is the 1 by k1 value, right? Plus T2 square upon 4 pi square m. It will cancel out. So T1 square is equal to T1 square plus T2 square. So the new time period of oscillation in this case, when the springs are connected in series, will be square root of T1 square plus T2 square, right? Copy this. So read this question. In this question, the infinite spring of the spring constant K, 2K, right? This is K, suppose this is the 2K, this is 4K and then 8K respectively. They are connected in this way, right? So you have to find the K equivalent. So what is the K equivalent, you tell? How to find the K equivalent? 1 upon K equivalent is equal to what? 1 upon K1, 1 upon K2, 1 upon K3, 1 upon K4 and so on. If you take 1 upon K common, 2 square, 2 cube up to infinity. What is it? You tell. It is the infinite GP. Infinite GP. What is the sum of infinite GP? Is equal to A upon 1 minus R. What is the A over here? A is the first term, which is equal to 1. And what is the R? Is the common ratio. It is 1 by 2. 2 minus 1 is equal to 2. Is equal to 1 upon K into 2. So the K equivalent is K by 2. So this is the answer, right? Copy this fast. So now we will discuss the different cases of the pulley and spring block system. The case 1 I am discussing, right? The case 1. Although you can put the values and get the answer. The case 1 is that, suppose this is the pulley, right? And there is a spring which is attached to ground like this, and this is the mass m. Are you getting or not? Right? You tell me. Now if it is displaced little bit and it will start oscillating, you have to find the time period. Although you must remember, if this is the spring pendulum, right, the constant K, are you getting? The time period is what? Say 2 pi root m upon K. Now in the different cases, this is the one figure, the next and next figure. In 3 figure we will discussing the time period of oscillation in this case. Listen one thing. First of all, what you have to do, suppose there is no elongation in the spring constant K. So when you have to find the time period of oscillation, right? So what will you have to do? First you have to find the equilibrium position. So to find the equilibrium position, when it will come down, right? Suppose this is the spring. So there will be some elongation in the spring, right? And the block will come little bit down. Are you getting or not? So this is the elongation, right? In the spring, elongation is x naught. In this case, this is the equilibrium position. In this case, the mg force and kx naught will be same. Mg is equal to kx naught, right? And it will be at rest. So find first equilibrium position, then give the small displacement x, either in upward direction or downward direction. So if you release, if you pull it down further by distance x, right? By distance x, right? So there will be some elongation in the spring again, right? And you have given a small displacement x further, right? So you tell me how many force are acting? Mg. And the elongation in this spring, this is the mean position or equilibrium position, right? The spring in this is the elongation will be x naught plus x. So what is the spring force? Listen one thing, this is the spring force. You are getting this thing or not? This is the spring force, right? Fs, like this, and Fx, the x naught is the elongation, the kx naught is the spring force. Now if you further move it down, the elongation in the spring is x naught plus x. So what is the spring force this time? The spring force this time will be equal to kx plus x naught. Are you getting or not? In this case, you tell me. This force here, the kx naught and mg are equal. Here kx plus kx naught and downward force is mg. So acceleration will be this direction or not? So what is the net force here? The net restoring force is equal to kx plus x naught minus mg is equal to kx plus kx naught minus mg. All right, it will cancel out because both are equal. Minus m into a, acceleration is equal to k by m. Many times we have done omega square is equal to k by m. So t is equal to 2 pi root m upon k. Also from here, k is equal to m omega square. This relation is very useful sometime. So what is the time period of oscillation for this system? 2 pi root m upon k, as it was found in this case, but not always. In further cases, it will be different, right? First copy this. So listen one thing, although it is a very long method to solve this question, I am giving you the shortcut, right? The shortcut is what? Simple. If initially we have found the equilibrium position and we give the elongation. In the equilibrium position, the net force is 0. Now you consider the block when it is in equilibrium. Suppose it is in equilibrium, right? So net force is 0. Now pull it down further by distance x. When you pull it down further by x, so what is the extra force acting on this? You tell me. The extra force or the restoring force, because it is the equilibrium position. If you move it down, so spring will elongate it by the same distance x, and the extra restoring force is what? Restoring force is nothing but equal to kx. You will write directly. This is the restoring force kx acting upon this, and this is equal to minus m into a, k into x. So acceleration is k by m into minus x. Compare with this equation and you will get omega square is equal to k by m and t is equal to 2 pi root m upon k. So this is the shortcut. Further, in further question we will do in the same technique, otherwise it will take a long time, right? First find the equilibrium, then give the displacement, find the net force, although it is the correct way, right? But we can do also in this way. In the equilibrium position, give some displacement, find the restoring force, put equal to minus ma, then you will get your answer, right? Copy this fast. So the next case too you can consider. Suppose this is the pulley, right? This is the pulley and the spring is connected here. The mass is connected in this way. Are you getting or not? Like this. So when it is, this is the movable pulley, right? When it is pulled down, right, little bit, small displacement, and then it will oscillate. You have to find the time period, right? Now, as I told you, right, what you have to find, you have to consider this the equilibrium position. Equilibrium position means the net force on this 0. Now, if you displace by distance x, little displacement you give, right, and you have to find the restoring force. Are you getting or not? Listen one thing, when you give the small displacement in downward direction, the pulley will come down also. Are you getting? And this spring is elongated. So if it is moved by distance x, what is the elongation in this spring? You tell. If it is moved by x, what is the elongation? Right? This is the pulley constraint method we have done in the Newton's laws of motion. Right? How to solve this question? Let's see this side. Listen, if this is the pulley, right? Suppose it comes down by 1 meter, right? Like this. If this pulley come down by 1 meter, right? Initially the system was like this, right? This is the mass M over here. If pulley come down by 1 meter, so this is the 1 meter, 1 meter. So what is the distance moved by the M? You tell. If pulley come down by 1 meter, this is the 1 meter string, this is the 1 meter string, the situation become like this, right? The situation become like this, right? You tell. Initially the block is over here. What is the displacement in the block now? Yes, Varsha, it is 1 meter. So this 1 meter pulley, 1 meter string and 1 meter string, right, right, unbounded, and it moved by 2 meter. Is it clear or not, you tell? If pulley come down by 1 meter, what is the distance covered by the block? It is 2 meter. Is it clear or not, you tell? Right. So it means if it comes down by the x meter, right? So what is the distance moved down by block? Say 2x meter. Is it clear or not? If it come down by x meter, the mass will move down by 2x meter. In the same way, if the mass is pulled down by x meter, what is the elongation in the spring, or what is the distance moved by the pulley? Is the same as the elongation in the spring. So if it is down by x meter, the elongation is x by 2. Are you getting or not? Right. So therefore, what is the spring force over here? The spring force is kx by 2. Are you getting or not? This is kx by 2. Fine. Now, what is the restoring force? Suppose this is the restoring force. Suppose this is the tension. Tension is the restoring force now. This is T and T. So, for the pulley, the above force is kx by 2, up force, and this T plus T. So, this is equal to 2T. So, what is the T? Kx by 4. So, what is the restoring force now? Restoring force is nothing but equal to T, which is equal to kx by 4, right? And the acceleration will be in this direction, minus m into a is equal to kx by 4. So acceleration is k upon 4m minus x. Therefore, acceleration is proportional to minus x, motion is SHM. Compare with this equation. The omega square is equal to what? K by 4m in this case. Fine. Omega is equal to 1 by 2 root k by m is equal to 2 pi by t, and t is equal to 4 pi k by m. Is it clear or not? So in this case, when the spring is connected between pulley and this point, in this case the time period of oscillation will be 4 pi root k by m. All right, copy this. So in the case third, right, this is the movable pulley, right, and the on one side there is a string and there is a spring, right? This side the spring is connected, all right, like this, and the mass m is connected. Suppose it is in equilibrium, it means there is a already elongation is present such that the net force in equilibrium, right? So to prove that it is SHM, or to find the time period, although it is SHM, to find the time period you will give the small displacement x, right, and find the restoring force. The restoring force will be T dash over here, right, or you may assume this T. So you tell me, listen one thing, if this spring, right, if this is there is a displacement in the block x downward, what is the elongation in this spring? Can you tell? What is the, if it is x, what is the elongation in this spring? How to find? Listen, we do reverse process. If this, right, remove this, if this pulley goes up by 1 meter, right, are you getting or not? If this pulley goes up by 1 meter, right, so this is the 1 meter, this is the 1 meter, the spring is compressed by 2 meter. I think it is clear. This is the 1 meter, this is the 1 meter. So you can assume like this, right? This is the 1 meter, 1 meter. If it is move up by 1 meter, this 1 meter, 1 meter, it is again compressed, right? If it is come down by 1 meter, the elongation in the spring is what? 2 meter, right? So if it is goes up by x meter, right, x meter, what is the compression in this spring? Say 2x meter. Are you getting or not? Right. Further, if it comes down by x meter, what is the, if this pulley come down by x meter, are you getting or not? What is the elongation in this spring? Say 2x meter. So if this m mass is moved down by x meter, the elongation in this spring is what? Say 2x meter. So this is the process to find this. I am explaining it. Initial there is a pulley, right? This is the pulley. If this 1 meter, 1 meter, it move down, move up. So this 1 meter and 1 meter, the spring is compressed by 2 meter. So therefore, if it is come down by 1 meter, the elongation in this is 2 meter. If it is come down by x meter, the elongation in this spring is 2 meter, 2x meter. So if this mass is come down by x meter, this pulley also come down by x meter. So the elongation in this spring will be 2x meter. So look at the figure. The spring force is what? K into x. Here also this is the one string. So 2kx, and here also 2kx force. So this force is what? This force is also 2kx plus 2kx is equal to 4kx. So this tension, the restoring force this time is nothing but 4kx, right? This is equal to the restoring force. Minus m into a is equal to 4k into x. Acceleration is 4k by m minus x. A is proportional to minus x. Motion is SHM. Compare with the standard equation of SHM, right? The omega square is equal to what? 4k by m. Omega is equal to root over 4k by m is equal to 2 pi by t. T is equal to 2 pi root m upon 4k. It comes out from the square root m upon k. So the time period in this case will be pi root m upon k, right? Copy this.